In this lecture, I will present the section about the relationship between load and loss factors, which is part of the load characteristics chapter. Which is the third section in the load characteristics chapter. Let's assume that the primary feeder shown in this figure is connected to a variable load P. Its arbitrary and idealized load curve is given, as shown below. Notice that the load is represented by only two states, and alternates between peak load value P2 and off-peak load value P1. Notice that the load is represented by only two states, and alternates between peak load value P2 and off-peak load value P1. Recall that the load factor is calculated as the ratio of the average load over the maximum load, which is in this case the peak load P2. However, the average load in this case can be calculated as the sum of the peak load multiplied by the time, small t, and off-peak load multiplied by the remaining time of the period, capital T minus small t, divided by the total time period, capital T. Now, substituting the expression of the average power into the expression of the load factor, yields this new equation of the load factor. This equation can be developed further, to obtain this new equation of the load factor, which is expressed as a function of P1, P2, the total period, and the time duration of the peak load. Let's assume that the off-peak loss is PLS1 at some off-peak load P1, and that the peak loss is PLS2 at some peak load P2, as shown in the figure. The loss factor is defined as the ratio of the average loss divided by the maximum loss, which in this case is peak loss PLS2. In this equation, PLSAV designates the average power loss. PLS max designates the maximum power loss. And PLS2 designates the peak loss at peak load. From the figure, we can also obtain the following equation of the average power loss, as function of the peak and off-peak losses, the total period, and the time of the peak loss. Then, by substituting the average loss expression into the previous loss factor equation, the following new loss factor equation is obtained. Where PLS1 is the off-peak loss at off-peak load. T is the peak load duration. And capital T minus small t is the off-peak load duration. We know that the copper losses are functions of their associated loads, so we can write PLS1 equals K times P1 square, and PLS2 equals K times P2 square. Recall that the ohmic losses are proportional to the square of the current, while the loads are proportional to the current for a given voltage. That is why the loads are squared in these relations. Thus, by substituting the expressions of the losses as a function of the loads into the previous loss factor equation, we obtain the following new equation of the loss factor. The above equation can be rearranged to obtain this new equation of the loss factor. Notice that the proportionality factor K has disappeared from the equation, which gives a new expression of the loss factor as a function of the peak and off-peak loads. Now, rewriting the load factor equation and the loss factor equation next to each other, we can notice that there is a possibility to find a relationship between them. Indeed, the load factor can be related to loss factor for three different cases. Let's start by considering case 1, where the off-peak load P1 is 0, therefore, the off-peak loss PLS1 equals 0, since P1 equals 0. Thus, The load factor relates to the loss factor as given by this equation. That is, the load factor is equal to the loss factor, and they are equal to the peak time t over the period t, which is constant for a given peak time and period. For case 2, we consider a very short-lasting peak, that is t nearly equals 0. Then, we have t minus t, and over t, is nearly equals to 1. Therefore, the value of the loss factor approaches the value of the load factor squared. For case 3, we consider that the load is steady. That is, the peak load time t is nearly equal to the total period t. It means that, the difference between peak load and off-peak load, is negligible. Thus, the load factor is nearly equal to 1. And the loss factor is also nearly equal to 1. That means that, the value of the loss factor, approaches the value of the load factor. Therefore, in general, the relationship between loss factor and load factor can be expressed as follows. The loss factor ranges between the square of the load factor and the load factor values. Recall that both FLD and FLS are less than or equal to 1. An approximate formula that relates the loss factor to the load factor is found empirically as follows. For the case of urban area, the loss factor equals 0.3 times the load factor plus 0.7 times the square of the load factor. And for the case of rural area, the loss factor equals 0.16 times the load factor, plus 0.84 times the square of the load factor. Note that, in both empirical equations, the loss factor and load factor are expressed in per unit. This figure shows the plots of the loss factor versus the load factor for the different special cases, and also the general one. The upper blue linear curve is for cases 1 and 3, while the bottom red curve is for case 2. The orange curve is for the general case of urban area, and the magenta curve is for the general case of rural area. Notice that the curves of the general cases lay between those of cases 1 or 3 and 2. Now, let's practice on few examples. In the first example, we consider that the average load factor of a substation is FLD equals 0.65. We want to determine the average loss factor FLS of its feeders, if the substation services A. an urban area, and B. a rural area. To solve this problem, we can proceed as follows. We know that, for an urban area, the empirical equation is as shown here. Since we are given the load factor of 0.65, then it is possible to substitute its value into this equation, to find the loss factor for urban area, that equals to 0.49 per unit. Similarly, for the rural area, we use the corresponding empirical equation and substitute the load factor by 0.65 in this equation, to find the loss factor equal to 0.53. In the second example, we assume that a distribution substation is supplying a small town with a monthly maximum load profile shown in this figure. This distribution substation experiences an annual peak load of 3,500 kilowatts during the month of August, which is mainly due to air conditioning load. The total annual energy supplied to the primary feeder circuits is 10 million kilowatt-hour, or 10 gigawatt-hours. We want to find A. the annual average power demand, and B. the annual load factor. To solve the first part of this problem, we first start by calculating the annual average power demand, as the ratio of the total annual energy, over the total number of hours per year. That is equal to 10 million kilowatt-hour, divided by 8,760 hours per year, which equals 1,141 kilowatts. In the second part, we need to calculate the annual load factor, that is the ratio of the annual average load over the annual peak load. That is 1,141 kilowatts divided by 3,500 kilowatts, which equals 0.326 per unit. For the calculation of the loss factor, we use the rural approximate equation relating the loss factor to the load factor. Thus, the loss factor is in this case 0.141. A third example is considered, where we assume that the annual peak load input to a primary feeder in urban area is 2000 kilowatts. A computer program that calculates voltage drops and copper losses shows that the total copper loss at the time of peak load is 100 kilowatts. Knowing that the total annual energy supplied to the sending end of the feeder is 5.61 gigawatt-hours, we need to first determine the annual loss factor, and second, calculate the total annual copper loss energy and its value at 6 cents per kilowatt-hour. To solve this problem, we start by calculating the load factor. The load factor FLD equals the ratio of the annual average load of 5.61 gigawatt-hours divided by 8,760 hours per year, over the annual peak load of 2000 kilowatts, yielding the value of FLD equal to 0.32 per unit. Thus, the annual loss factor for the urban area can be approximated using the corresponding empirical equation, which yields a value of FLS equal to 0.1677 per unit. In the second part of this problem, we were asked to calculate the total annual copper loss energy, and its value at 6 cents per kilowatt-hour. For that, we use the definition of the loss factor, and deduce the annual power loss, which equals the loss factor multiplied by the power loss at peak load. That is, 0.1677 times 100 kilowatts equals 16.77 kilowatts. The total annual copper loss energy equals 16.77 kilowatts times 8,760 hours per year, which yields a total annual copper loss energy of 146,905 kilowatt-hour. Knowing that the cost of energy is 6 cents per kilowatt-hour, we can calculate the cost of the total annual copper loss, which equals to $8,814. In the next example, we assume that one of the distribution transformers of a substation supplies 3 primary feeders. The 30 minutes annual maximum demands per feeder are listed in the following table, together with the power factor, PF, at the time of annual peak load. We assume a diversity factor of 1.15 among the 3 feeders for both real power, P, and reactive power, Q. We need to first calculate the 30 minutes annual maximum demand on the substation transformer in kilowatts and in kilovolt amperes. Then, we find the load diversity in kilowatts. Then, select a suitable substation transformer size, if zero load growth is expected, and if company policy permits as much as 25% short-time overloads on the distribution substation transformers. Among the standard 3-phase transformer sizes available, are the following: 2500 kVA for self-cooled and 3125 kVA for forced air-cooled transformers. 3,750 kVA for self-cooled and 4,687 kVA for forced air-cooled transformers. 5,000 kVA for self-cooled and 6,250 kVA for forced air-cooled transformers. 7,500 kVA for self-cooled and 9,375 kVA for forced air-cooled transformers. Finally, we assume that the substation load will increase at a constant percentage rate G per year, and will double in 10 years. If the 7500/9375 kVA rated transformer is installed, in how many years will it be loaded to its fans-on rating? Note that the term fans-on rating means the forced air-cooled rating. Now, to solve this problem, we start by question A, in which we are asked to calculate the 30 minutes annual maximum demand on the substation transformer in kilowatts and in kilovolt amperes. We first determine the coincident maximum demand of group of loads DG, by considering the equation of the diversity factor FD, and using the demands per feeder DI, as given in the previous table. We know that the diversity factor FD should equal 1.15, hence, we can find the coincident maximum demand of group of loads as 6,000 kilowatts divided by 1.15, which equals 5,217 kilowatts. To find the apparent power in kilovolt amperes, we use the following equation. According to the given table, we can calculate the apparent power of each feeder and then calculate the total maximum apparent power demand, which in this case is equal to 6,692.1 kVA. After that, we calculate the coincident maximum demand in kilovolt amperes, by dividing the calculated maximum apparent power by the diversity factor, which yields a value of 5,819.2 kVA. In the second question B, we are asked to find the load diversity in kilowatts. Using the definition of the load diversity, we can determine its value by summing all three feeders' maximum demands, and subtracting the coincident maximum demand DG in kW. So we have 6,000 kilowatts minus 5,217 kilowatts, which equals 783 kilowatts. In the next question C, we are asked to select a suitable substation transformer size, considering that the transformer can be overloaded for a short time, to 125%. Which means that we divide the coincident maximum demand, S equals 5,819.2 kVA, by 1.25 to account for the 25% overload, which yields a value of 4,655.4 kVA. From the given transformer list, it is appropriate to choose the transformer with the 3,750/4,687 kVA rating, since its forced air-cooled rating is slightly larger than the coincident maximum demand. In question D, we need to determine how many years will this transformer be loaded to its fans-on rating, considering a constant yearly increase G, and reaching a double value in 10 years. Note that the term fans-on rating means the forced air-cooled rating. To find the load increase, G, per year, knowing that the load will double in 10 years' time, we can write that 1 plus G, power 10 is equal to 2. Which means that 1 plus G equals 1.0718. Therefore, G equals 7.18% increase per year. In the next question, we would like to know, if the 7,500/9,375 kVA rated transformer is installed, in how many N years will it be loaded to its fans-on rating, which means his rated power of 9,375 kVA. For that we write, 1.07175 power N, multiplied by 5819.2, that equals 9375 kVA. Which implies that 1.07175 power n equals 1.611. Thus, n equals log 1.611 divided by log 1.07175, that equals 6.8817. The closest higher integer value is, n equals 7 years. Therefore, this means that, if the 7500/9375 kVA rated transformer is installed, it will be loaded to its fans on rating, in about 7 years. This is the end of this lecture, and also the end of the first chapter. I hope that it was clear and informative. Thank you for watching.